Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the fifth in the series on design end-to-end. In the last video, I completed the initial design of the indicators function block. Now, if you've missed that video, I put a link to it up in the corner for you. In this video, we're going to cover the initial design of the final function block, the power function block. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. Now, let's dive into the power function block. Well, this guy feeds everything else, so we have to think about everything else when we make decisions about this. One of the first things that we have to protect against is reverse input voltage. Now, there's quite a few ways that we could approach this. We could use a simple diode in series with the input. But diodes have a decided voltage drop, which changes with the current that's passing through it. Now, a Schottky diode has a lower voltage drop than regular diodes, so if we choose this particular option, using a Schottky diode would be a good choice. I've also seen folks use a diode bridge so that the input, well, didn't care how you wired it. It just worked. These also experience the same voltage drop issue that this simple series diode exhibits, only twice over. Now, this is my favorite approach because it does not have as high of a voltage drop of either of the diode approaches. It uses a single P-channel MOSFET. So how do you design this in? How do you choose that device? Well, you must choose a device whose maximum gate voltage is above the maximum input voltage of the design. It needs to have an internal gate to source diode, and it also has to have a current rating which significantly exceeds the anticipated current that will be drawn by your design. Now, I'm going to use an ON semiconductor NTR0202PLT1G. It's rated up to 20 volts gate voltage, good for this design, and 400 milliamps of continuous drain current. We're not going to be going anywhere near 400 milliamps. Next, we begin considering what the input voltage is going to be. Yes, well, it's a nominal 12 volts. But it could sag, or it could be higher than this. We want to make our product as immune to supply voltage variations as possible, which means that we want to be able to tolerate as low of an input voltage as possible without impacting the operation of our product. What we have to design here is the means of providing the power that's going to make everything work. Originally, I was going to have the entire design operate off of a single positive supply. But I've changed my tune on this because of the situation with the indicators function block. This means that we need both a positive and a negative power supply of equal voltage. But we're faced with a problem. We only have a positive input voltage. How on earth do we create a negative supply from a positive supply? Well, there's a few solutions to this. And one of these solutions is what's called a charge pump voltage inverter chip. This takes a positive input voltage and turns it into a negative voltage, like the Max 860. Or even a dual regulated version like the LTC 3265. The other option is a genuine switching regulator, which will do the same thing. Yet one more option is what some might call the lazy engineer's option, a ready-made, completely self-contained power supply module, which takes the nice DC input voltage and creates the dual supply voltage that's needed. And you know what? That's exactly what I'm going to do with this project. The question that we have to answer first is, what does my power supply voltage need to be? So let's just step back from the whole design for a moment and take a voltage inventory. The output of the various amplifiers reach a designed maximum of plus 10 dBu. Doing the math, the peak voltage amounts to 3.464 volts. We figure in the fact that the chosen op amps need at least 0.22 volts of headroom. Our power supply has to be no less than 3.68 volts. So based on this alone, 5 volts seems sufficient. But we can't stop here because we have indicators function block, which also uses op amps to run the output level meter averaging amplifier. Now the averaging amplifier has gain to it that we need for the comparators. The highest level LED is plus 3 dBu, but we need to be absolutely linear to this point for the meter to actually mean anything. So I'm going to add another 3 dB to this and shoot for plus 6 dBu. At plus 6 dBu, the output of the averaging amplifier will be right around 8 volts-ish. The op amp wants that additional 0.22 volt headroom, so our minimum power supply voltage would be 8.22 volts. Now on this basis, I will choose to shoot for a 9 volt power supply. This also means that we will need a minus 9 volt power supply as well. So rummaging around in DigiKey, I find a CUI or CUI PQP1-D12-D9-M DC to DC converter module. It will supply plus or minus 9 volts up to 56 milliamps. The caveat is that it requires a minimum current of 2 milliamps at all times. Well, this is easily taken care of on the positive side with the voltage dividers. We have 4 of them, and each of them draws 1 milliamp. But we need to add a resistor to the negative side to match this, so we have 4 milliamps at 9 volts, which gives us 2.25 k ohms, and a standard resistor value is 2.26, so that's what we'll use there. Then there's some more good news about this great little module. It tolerates input voltages from 9 to 18 volts. Wow, that's a really nice input voltage range. Okay, so it cost $8.56 a piece. But from my perspective, it's worth every penny. Now we have to consider what components have to be put in place around the device. To do this, I will look at the data sheet to see what their recommendations are. And, well, they're pretty simple. We will put a 47 microfarad capacitor on the input as close to the input pins as possible. Now I'm going to parallel this with a 0.1 microfarad capacitor to catch any high frequency stuff that might try to escape. With up to 18 volts in, these capacitors should be rated at no less than 35 volts. What they show for the output, though, is a bit confusing. First, they don't list the 9 volt guy in their capacitor tables. This kind of leaves us guessing. Second, the illustrations don't seem to directly apply to the dual output model that we're using. So I'm going to make an educated engineering guess. I'm going to put a 47 microfarad capacitor between the 0 volt terminal and each of the outputs. With the outputs being 9 volts, this capacitor must be rated at no less than 18 volts. And with the closest standard voltage to this is 25 volts, so that will be my choice. Now, if I really want really clean DC, I'm going to add an additional 0.1 microfarad capacitor across each of these to catch the high frequency stuff. And this capacitor will be located as close to the device pins as possible. And all of this brings up the power supply feed to the op amps and comparators, at least in my mind anyway. Each op amp and comparator chip's power supply pins will be bypassed with both a 10 microfarad capacitor and a 0.1 microfarad capacitor as close to the power supply pins as possible. So, the initial design of the power supply function block is now complete. But you know, I did say in the previous video that I would show you how to provide that pseudo-ground voltage without using a regulator to do it. And while the need for it no longer exists, I will make good on that promise just now. So here's how we're going to do this to ensure that the voltage actually follows the power supply voltage. We start with a resistive voltage divider whose output is heavily filtered with a capacitor. This voltage must be nice and clean and stable. The resulting voltage is the input to a non-inverting buffer amplifier stage using a single op amp. The choice of the op amp really isn't critical. I mean, you could use an on-semiconductor. Here it comes, NCS20071SN2T1G. It comes in a nice SOT23-5 package, easily soldered by hand. At DC, it has a very low output impedance and will provide that VCC over 2 voltage that you need while absolutely following the power supply voltage variations. We have completed the initial walkthrough, the entire design. We're ready to begin putting all of this into an official schematic from which we derive the PCB layout. In the next video, my plan is to introduce you to what is called schematic capture. The package I choose to use, because you can get a free version of it, is DipTrace. I've put a link to the free download down in the description for you if you want to download it and install it to get a leg up on the video. If you found this video helpful, please click on the like and subscribe. Thank you so much for watching. Until next time, toodle-oots.